The physics of ice dancing. The concepts I used were the laws of motion, fluid dynamics, energy, momentum, and rotational motion. The importance of the law of motion I used, which was Newton's third law of motion, is that it's relevant in all movement. The fluid dynamics are important because it makes ice skating even possible. Energy transfers are used to maintain the movements, especially jumps. Momentum is needed to maintain the stunts, and without it, a lot of times people create falls or get extremely injured. Rotational motion is important because it's used to do multiple tricks. The physical variables that were included: the main factor is the person themselves. Without them, there would be no variable. A lot of times they have a partner or a second person. The leg muscles of the skater house a lot of the energy, especially potential energy. Physical variables continued. The ice itself is another physical variable that is the entire sport. The skates and their shape play an important role, especially with the bladed edge and the picked tip. They allow for the skater to move across the ice smoothly and pick up on the tricks a lot more easily. Finally, their uniform itself is another factor that plays into the physics of it because they are aerodynamic and light. If they were any heavier or if they had more fabric, it would create way more wind resistance. The relevant formulas I used were mainly for momentum and rotational motion. I used the formula for moment of inertia, which is mass times the distance squared. I used angular velocity, which is 2 pi divided by the period or the rotations per second. I used angular momentum, which is the two previous equations multiplied together, or the moment of inertia multiplied by the angular velocity. And I also very slightly used the linear velocity, which is the angular momentum times the radius or the distance. That concept continued. I used the equation for force, which is mass times acceleration, but because it was with two masses and it was angular acceleration, I used mass 1 plus mass 2 multiplied by the angular velocity squared times the distance. Energy was also a big factor in this, and I used kinetic energy, which is 1/2 the mass times velocity squared. I also used potential energy, which is mass times gravitational acceleration times height. Now to the applied physics. Newton's third law of motion was applied throughout the entirety of the sport. Just to elaborate on what that is, it is that every action has an equal and opposite reaction, which we all know. It is responsible for the force that pushes back on our feet when we walk, and it is no different with the skates. I also used fluid dynamics, which is not really a concept we studied, but it is the study of liquids in motion. Water itself has a specific special quality, and when it is ice and it is pressurized, it becomes water no matter the temperature. So under freezing at 32 degrees Fahrenheit or 0 degrees Celsius, if you apply pressure to the ice, the very top layer of it will become water, which is crucial for skating because it creates the lack of friction where they can slide around. So if you didn't have the special skates on, you would slip and slide everywhere. Energy. The use of energy mainly applies to just the transfers between kinetic and potential. The main transfers of energy were applied, at least through my essay, throughout the jumps that they make. During the jumps, there's specific energy shifts that shift from potential to kinetic, which make the jumps even possible. First, when moving, the energy is potential within the skater's muscles, but as soon as they make the leap, the energy becomes kinetic. As they make the leap, the gravitational potential energy is increasing and is swapping with the kinetic energy. And at the height of the jump, there is zero kinetic, and all of the energy is gravitational potential energy, since gravity is now acting against the skater and is pulling them back towards the earth. Once the height of the jump has been reached, the kinetic energy is now back as a force, but not as much as gravitational potential energy. Once the skater reaches the ice, all of their energy becomes kinetic until they are finally 100% back on the ground. Momentum, which is basically just mass in motion, is applied during jumps, spins, and other tricks, and is characterized as usually being in RPMs or rotations per minute. When a skater makes majority of their spins, they pull their arms and leg, their free leg, in towards their body. When a skater spins and pulls both of their arms and their free leg in to spin faster and faster, it is caused by the conservation of momentum. This is where rotational inertia is reduced and their speed increases in order to maintain the constant angular momentum, making this a crucial part in most skating routines. This is also characterized by inertia, where an object in motion tends to stay in motion. A small bit of force or torque is used to generate the initial momentum, and then they will pull in to keep going faster. And this is where the moment of inertia formula is used. As previously explained on the last slide, rotational motion is essentially angular momentum, which is conserved when the skater pulls their arms in and creates their own speed. The speed of the skater and the inertia of the momentum are factors in this rotational motion. In order to stop this motion, the skaters will open their arms and their free leg, moving them back away from the body in order to slow down or to land their tricks. Inertia plays a large role in the dancer's rotational motion, where the mass is needed to rotate around an axis, also known as the moment of inertia, which we previously talked about, which equals the mass rotating around the axis at a distance or a radius, multiplied to represent the formula I equals mr squared. And the angular velocity plays a role, which is represented in revolutions per minute or radians per second, where one cycle is equal to 2 pi radians. And when multiplied by the moment of inertia, it gives you the angular momentum, or the rotational motion. A spinning figure skater literally has little to no friction between them and the ice, which nearly conserves all of their angular momentum. The only thing that keeps them having friction is their special skates. And these are the sources that I used.